going, I think it's going to help. You know, if you can just plug it in, plug it in. If you can factor and simplify, do it. Rationalize, simplify, do it. With trig, though, it's like identities can be really helpful. And of course, looking for those two limits that we looked at the last couple days. All right, sine theta over theta, and then 1 minus cosine theta over theta. As we go to 0, it's all about going to 0. I think we at least got onto this second page. So I'll leave up 6 and 7, but I'm happy to scroll to whatever you need. So let's have a day. Anybody else get that weird clicking sound? Oh, my head. Get that a little higher. Just push it back a little bit. There we go. So yeah, folks at home, just let me know what you need. If you want to look at anything. Which one? The first, which page? 52? Yeah. Yep. There you go. So first one's just direct substitution. Don't have to worry about anything. With like 2, 3, and 4, I'm really like I'm taking that constant and it's not really factoring because it's a limit. I can't like factor things out of a limit, but they're equivalent. So like I factor out the 4 from the top, I can factor out the 1. I mean, it's not really 1, but just so we see it. Because if and it's very informal, but it works the same way. So we're okay to do it. I can just pull out that 4 over 1. And then that limit is always 1. And so same thing here. Like I'm taking the 2, taking the 3. Use that one. Use that one. Either one of those over there work.
That one over there also. Wait, there's another one?
There's 2 of them. That's kind of my thought process on that. And that's a nice thing about some of these limits is, that's yours, by the way.
Oh, we're not worried.
Yeah. I'm just kind of isolating that limit because I know that's going to be one. But you don't have to write it like that. You can write it how I did. If you recognize that limit, just go right to the constants product. Because I am taking out the 2, taking out the 5, taking out the 3. 2 times 5 over 3 times that limit. Because once I pull out those constants, there's our limit that we're searching for. And that's just 1. What's up, man? 5? Okay. So, with something like 5, of course, and with all of these, I'm always going to try to plug it in, see if I can. But I know plugging in 0 is going to give me 0 over 0. So, I can't use direct substitution yet, but I can see if there's a way to like factor and divide or simplify or do something. And so I just kind of get started by looking for anything to factor. I mean, something like 5 on page 55, the only thing I can factor out is the x. That's in common denominator. But once I did that, I said, oh, well, wait a minute, hold on. Look at that. Sine of x over x, that's what I'm looking for. And so the kind of skills that we're starting to acquire here with this last part of unit 1 is trying to look for those limits that I can either separate with multiplication or separate with addition or subtraction. And so since I factored and rewrote the denominator as multiplication, I got to just keep splitting things apart with multiplication. So I turn that one fraction into 2 by pulling out the limit that I know I like, which is the sine of x over x, and then just try to figure out what I have left for the second fraction. The limit of the product is the product of limits, so I can deal with those two separately. And by factoring and splitting it apart, I've actually pulled out the problem, which was the x that was on the bottom that was in common. That's what was making it 0. And that's what I want to avoid, dividing by 0. So, all right, well, let me pull out that limit, which is just 1. And then I can just substitute directly to find the limit of the second one, and there we go. And so 5 and 6 are good examples of the kind of things that we're going to do separately, either like factor, and if it's not factored yet, and then break it apart with multiplication, or recognize addition, or subtraction, in this case addition, and just try to deal with those limits separately. Because with like number 6, like these x's cancel, which is awesome. And, you know, pull that 3 out right there, pull the 1. Obviously, you don't need to pull the 1 out, but we do anyway, just to really drive the point home early on anyway, so you guys can see that. Limit of a constant is just that constant, and there's the limit, 3 over 1 times 1. Really, that's what's happening, right? The limit of sine of x over x. And that's approaching 0. Yes, there we go. Turn up the volume. So what's happening kind of in between here when I pull out that? So like imagine there's an equals right here. So I've got that limit of the constant. And then I can pull the 3 out and the 1, but it's a straight over 1, so write it if you want. But like that limit that's left behind is that. Again, we're always looking for, if we can, either the sine of x over x limit or the 1 minus cosine of x over x, or theta, if you're on any side to use. But you don't have to actually write that step. We've proven it to ourselves that that limit is 1. We've proven to ourselves that if you just have constants being multiplied, either like in front of the sign, inside with the x, on the denominator, whatever, that the limit of that function will always just be the ratio of those constants. You just pull them out, multiply tops together, multiply bottoms together, whatever you get, and that's going to be your limit. So if you recognize that from the beginning, then you don't have to write that step in blue where you factor the 3 out and then rewrite the limit. Like I did with like 7 and 8, pull out the constants, see what you get. Right? 7 and 8 is exactly what I'm doing kind of in the middle of that work for 6. Pull out the constants, take the limit right away. Knowing that because it's a limit of 1 and I'm just multiplying by 1, nothing's going to change about it. So I just pull out those nice constants and do that. So like what happens in calculus is like we learn it the long way. We try to wrap our heads around why the long way works, but we start searching for shortcuts right away. And once I learn a shortcut, I'm going to use it all the time. And that's what you're going to see. Chapter 2, chapter 3, chapter 4, as far as we can get, I'm going to like show you like the development of where the ideas came from. Newton was sitting there in his basement, sitting there by candlelight, just thinking this stuff through. Leibniz was going crazy doing the same thing. And they said novels and novels of work that ended with these like really simple conclusions that had really complicated reasoning behind them. He said, oh, well, that's why? Then let's just do it. And we're going to start doing that beginning of chapter 2. We're going to look at a very specific limit, just of like a function in general. Okay, cool. All right, well, this starts to develop a certain idea that I couldn't really attack before calculus. And we'll kind of explore that a little bit. But as we go through problem after problem after problem, we're going to start recognizing the same thing happening over and over again. Like, oh, here's my function. Here's the result from this calculus limit process. Is that true for all of them? And it's like, yep, works again, works again, works again. And oh, if that's the truth, then let's stop doing it the long way. Let's do it. We have to understand limits really well to be able to kind of believe that it's going to work no matter what we do. It does, which is really cool. And then like we never have to do it the long way again. We will always do it the short way. And then we build on that and build on that and build on those ideas. As the functions get more complicated, we always look for those nice, easy pathways to get to the right answer rather than doing it the long way and getting the exact same right answer. Just do it in 2 dimensions. And Calc BC starts to turn 2 into 3. Calc 3 is only 3-dimensional calculus. And then I stopped at Calc 4. That was enough. 4-dimensional calculus was enough. Which is just 3 dimensions moving through space and time. So you like study the calculus of the remote. And then you go like that. And you see what happens. So, a lot of connections to physics. Yeah, Porter.
Can we go up to 1?
Yeah. Now, here's the thing I said yesterday. It came up kind of at the end of class. I don't know if you guys caught it, but think about all of those like special trig limits, right? The sine of x over x or theta, whatever. 1 minus cosine theta over theta. Theta was always going to 0. That's what made those limits special. Look at this one on page, what was this, page 54? Look at what theta is going to in this limit. That is not 0. So I cannot go searching for a limit where theta is going to 0 if that's not the limit they're looking for. And so kind of recognizing that, like the difference between a question like number 1 and a question like number 2 here, is noticing that, yeah, number 2 is going to 0, so I'm going to start looking for those limits in case I can't do anything else. But number 1 is not going to 0, so those limit shortcuts are not going to do me any favors. So I don't necessarily start trying to isolate, sine of theta over theta if it was even there, or 1 minus cosine theta over theta, because theta is not going to 0. So it is super, super, super important that we pay attention to which x value, which theta value they want us to go to. So with this one not going to 0, I was like, all right, well, I don't need any of that. I'll just do some basic trig with some algebra, maybe some identities, and just see where it gets me. And the thing about number 1 that I didn't like right off the bat is that there were 2 different trig functions. One was cosine, one was sine. And I know I can't deal with those together at the same time, so I tried to get them down to just be sine or just be cosine. And so first line, a quick Pythagorean identity there, and see what it does for me. Oh, that's difference of squares. Sweet, I'll factor it. Ooh, I'm going to factor top and bottom, divide it away. Once I divide away the problem, then I should be able to just plug it right in, and it works. So what we've got kind of going on here is now a lot of different ways to deal with limits. Factoring, rationalizing, multiplying by conjugates, using identities if it's trig, and now looking for those trig limits, sine of x over x and 1 minus x. You don't really know what to start with every time. There's not always the same step 1. And that's okay. That's kind of the point in developing a different mindset in the way that mathematics is really done. I've said it before, I'm going to say it again. Everything you've done so far has been pre-mathematics, pre-calculus. Everything you've done has kind of led up to February 1st when we started this. So now we can really do math, which means we can really do physics for the first time. Now, like physics without calculus doesn't really exist. The study of space and time doesn't really exist without understanding calculus. So they're all connected. As much as it probably feels like you go from one class to the next, and they're very disjointed, right? I have to change my mindset. Oh, okay, now I'm going to English. I need an English mindset. See if you can start finding connections between classes rather than the distinction between them. And I think you'll feel like education is a little bit more worthwhile and less forced upon you. Because I always felt that way in high school. I felt like learning was being forced on me. And I'll quote Schitt's Creek because I was still watching this last night. I learn best when I feel like I'm not being taught a lesson. That's when I'm going to learn the most, when I don't feel like I'm being taught something. Paraphrasing, but that's very true. I'm always going to learn more when I feel like just like part of a conversation, not part of a lesson. Sure. So 3 is something that I keep kind of bringing up. I know we didn't talk about it very head on. It just didn't flow nicely with what we were trying to accomplish when we got to that point. So in the best way possible, I just keep trying to bring it in. So piecewise functions. So they're always, or most of the time, going to ask us for the limit at a spot where one function stops, the other one begins, right? Now, if that was the limit as x approaches 1, I would just pick the right function, I just plug it in, right? I pick the top one, because 1 is less than 3, and I just plug it right in. If it was the limit as x approaches 12, I would pick the bottom one, and I would just plug it in and see what I get. But because it's happening at the break point, where one function stops, the other one begins, what I want to try to figure out is, so from the left, where is it headed? From the right, where is it headed? If they're headed towards the same spot, the limit exists. If they're headed towards different spots, the limit doesn't. And so that's what I do. I check the limit from the left. Now, to evaluate the limit of a piecewise function from one side, I just go to that function and I plug it in. Knowing that I know it's not actually included, right? It's less than 3, not less than or equal to. So I know the point's not defined there, but remember, limits don't care about points actually being defined. They just want to know what y value we're getting close to. And so to do that, I can just direct substitution and see what would happen in case they were going to let me go there. So I plug in 3 into the top one. Why? No, that's only as you approach an asymptote. So the only time with one-sided limits where we actually plug in a number like just like a little before or a little after is when we're trying to decide if we're getting close to infinity or negative. Those limits from one side as we're approaching that asymptote, that's where that strategy comes in. Now, you could absolutely plug in something like 2.9 and then 2.95 and 2.99 and 2.999 and start inching your way closer to that spot and seeing if like the table of values approaches a certain spot. But because that function is like the top piece of that function is defined and continuous everywhere, it's just quadratic. I know it's part of a piecewise function and it's not defined at that spot, but when I consider what y value that function is approaching as we get closer and closer to 3, I can just plug in 3 and consider that the limit. And so that's what I do. I plug in 3 into the top one because that's less than 3, so that's from the left. I got 9. Then below that, I say, okay, well, I better see what's happening as I approach 3 from the right. Well, that's the bottom part of the function, that piecewise function. The 8 minus cosine of pi x over 3. And so that function's continuous. It's just a transformation of cosine. So it's going to be some kind of sinusoid. So I plug in 3 there and see what I get. And then I compare those two integers. I say, okay, the limit from the left was whatever it is. Oh, 9. Okay, just by plugging it in. The limit from the right, let's see what I get there. Ooh, that's also 9. The limit from the left is equal to the limit from the right, and they are 9. Therefore, the limit exists, and it is 9. So when you're dealing with piecewise functions at a breakpoint, and that's the limit that they want you to go to, plug it in the top, plug it in the bottom, see what you get. If they're the same number, there's your limit. If they are different, or one of them's undefined, or something weird happens in between, doesn't exist. Done. Right away, the end. Because they're asking me for that two-sided limit, right? In the original problem, it didn't say go from the left or go from the right. So that means I have to go from both sides. And so it's kind of like this 3-step process. Check it from one side, then check it from the other, and then compare. How we doing at home? All good? Questions? Okay, sweet. Let me know.
Can you go over number 5 on page 55?
Absolutely. Number 5. That one right there, sine of x over 2x squared?
Yeah.
Okay, so I look at the limit and it's going towards 0. So I try to plug it in, but it doesn't work because I get 0 over 0. And so it's all right, well, I can't do direct substitution. So let me try to mess with it somehow. Let me kind of alter the way it looks, and maybe I'll use identities, or maybe I'll divide stuff away. And really the only thing that I can do from the beginning that's going to at least get me started is look for something to factor, right? You've got this polynomial denominator, so I can't break up the fraction yet. So I factor. And the only thing that I can factor out of there, see if I can point at it while I'm sitting here, right, is that x right there, right? Because it's 2x squared minus x. So they have an x in common, so I pull that out, and I just, I see what I have left from pulling out that GCF. And then I just stop and think, okay, like, did that actually help? Did that do something worthwhile for me? If it did, great, I'll use it. If it didn't, then I'll backtrack and try something else. But what we notice What we're trying to find with limits where like x is going towards 0, theta going towards 0, whichever one, is one of those two really nice trig limits that we can use. Right, the sine of x over x or the 1 minus cosine of x. And there it is. There's sine of x over x. And so when I rewrite things factored, remember, like that's connecting things with multiplication. And so what I can do, and a really good strategy that we saw yesterday, and we're going to keep working on today, is breaking one fraction into two. Right, trying to split these fractions apart, isolating trig limits that I know I can use from the beginning. And there it is, sine of x over x. That, especially, right, because once I see x is going towards 0, that's an idea that just starts creeping into the back of my mind as something maybe to look out for. If that was x going to pi or pi over 4 or anything else, I wouldn't think about those limits because it's only about going towards 0 where that works. So I split the fractions into 2. All right, the sine of x over x comes out. 1 over 2x minus 1 left behind. The limit of a product is the product of two separate limits. This one can be evaluated right away. We know that limit. I don't have to worry about it. Sine of x over x as x goes to 0 is 1. And then this one, like by factoring out the x, which was the problem from the denominator because I was dividing by 0, and making that part of that first fraction that I can evaluate nicely, directly, by using that trig limit that's now proven to us, and now we can just use it. I've kind of pulled out the problem, right? The issue was having that x, and now I got everything else left behind. Hi, how are you? Sure, go for it. So now that that limit has been pulled out, now I can just evaluate this one directly, right? Direct substitution, I can just drop the 0 right there. When the 0 goes in, I drop the limit notation, and I just see what I get, right? Whatever happens by plugging it in, I'll see what I get.
That's D-E-N. What's your last name, son?
What's up, Luke?
What's happening?
Does that make sense, Keith?
Yeah, thanks.
8, 9, sure. If I did something right now, right? These two? So, so talk to me. Into 2 being added and subtracted. Okay. And so where did that continue there? Or did you just kind of get stuck?
And then the 2 boys in the back.
Right. And so, like, that's a really good initial thought, though. Like, single denominator, thinking added, subtracted up top, trying to break it apart with the subtraction. Never a bad first step. Just to kind of like, all right, so now what does that do? Does it look good? Can I isolate something? Can I, like, then what? No, because the x is buried in it. Now, what you like? So, what I think. Let's see. Let's pretend. Yep. Thank you, guys. See ya. Let's pretend if that happened and see what that could have done. So the limit as x goes to 0. So you had sine of x over x squared, right? And then minus sine of x cosine of x. Sine cosine over x squared. Now, okay, so if you broke those into 2, and I think we'll get there, it's just going to take longer. Because, all right, so now, like, I'll evaluate that one, and we'll see what happens. And so, like, by breaking them into 2 separate fractions, what you can try to do then is see if that got you anywhere. You say, all right, well, nothing I can cancel yet. Let me keep breaking them apart. Let me just look at this limit as if this was the only problem I had and see if there's a way for me to break that one fraction into 2. Now things aren't being added or subtracted over there, but I could write things with multiplication. And let's see if it does anything. Now, maybe it does, maybe it doesn't, but hopefully, like the kind of limit we're hoping to break it apart into is that, right? But then what's left behind is still that, right? And okay, cool, I'll break this, there's one, but I still can't plug it in. Right, so you might have like said, okay, this is my first thought, let me try breaking it apart. Okay, that didn't work, let me keep going and try breaking it apart even more. And eventually what you would hopefully at least try to do then is say, okay, this is now two separate limits. And you can see why this is not gonna work for us. Because the idea of like trying to break these limits apart is to try to like pull the problem out. Get rid of the problem by pulling it out. And so, yay, there's part of the problem gone, right? Because that limit is just one. If I plug in 0, now it's on the bottom. And so it didn't work. And so you might get to that point and say, all right, I tried everything. It's time to go back way up to the beginning and try something else. Okay, breaking it into addition and subtraction didn't work. Let me try from the beginning, breaking it into multiplication. By factoring the top, like that denominator of x squared is really the big problem because I can't divide by 0. Well, what do? Well, that means I have to get rid of both of those x's now, which means I need to kind of isolate them separately, x for one of them, x for the other, and see what happens. And by factoring first, I can take the sine of x and put it over one of the x's. 1 minus cosine x, put it over the other one. The limit of a product is the product of limits, and those are both of those trig limits that we now have proven that we can use right away. So when your denominator has like already factored, quote unquote, because it's just x squared, I know that, like for me, factoring is a great way to go. At least that's kind of what I'm thinking. Is that hand, Connor?
Yeah.
What's up?
Can you show me how to do 155?
Sure. Yeah, you're welcome. Direct substitution, babe. Just plug it in. Option number 1 is always, can I just drop it in and see what happens? Right? If it was just sine of theta on the bottom, all right, that'd be a problem because then I'd have 0 and that's no good. But it's sine minus cosine. And the only time those are the same, all right, 45 degrees and at 225, where x and y are the exact same values. So that'll be the only time subtracting them, right? Pi over 4 or 5 pi over 4, where I would actually get 0. So I'm going to 0. Sine is 0, cosine is 1, tangent 0. Direct. Now, that epiphany of just plugging it in took me like 2 minutes. Like I like sat down to do this problem, and I was like, what the hell am I supposed to do? I can't factor. There's nothing squared, so I can't use Pythagorean identities. Like I first tried like sine over cosine with the tangent. So well, that didn't do anything, just made things more complicated. I'll never be able to like, I had no idea what to do. Like I tried multiplying by the conjugate of the denominator. I tried like sine the theta plus cosine theta top and bottom, and that just got worse. I think that would have worked eventually because you'd have ended up with sine squared minus cosine squared. And I could have like tried a Pythagorean identity there, but then like the top got really messy. Like I tried this. I tried multiplying by sine of theta plus cosine of theta. Before I even realized that plugging it in wasn't going to be a problem. But then I ended up with, so the limit of blah, blah. So sine, right? 1 times sine, and then 1 times cosine, so plus cosine. And then negative tangent times sine, which is negative sine squared over cosine. And then minus another sine, because sine over cosine times cosine, so minus sine of theta. And I was like, oh, at least those canceled. That was nice. And it's going to work, but it took me forever to get there. I was like, why is this happening? So the denominator is sine squared minus cosine squared, because you're multiplying something by the conjugate, right? Then I created a common denominator up top by multiplying by cosine over cosine here. That gave me cosine squared minus sine squared, which was the opposite of, oh my God, like, I can do it. So check this out. It works, but it's super messy. So I multiply top and bottom by cosine of theta. Denominator stayed the same. The top of this fraction and the bottom of the main fraction are just opposites of each other. These, so like, all right, one fraction all over cosine, right? That was the whole point. These divided away to -1. Then I plugged in 0, got -1 over 1. I'm off the board, and I got -1. I was like, that was so much work and so sloppy and really messy. Let me just plug it in. Like, I stopped for a second, and I said, wait, what am I doing? Why am I going through this huge mess of multiplying by the conjugate, creating common denominators, having to recognize exact opposites, dividing those away, ending up with -1 over cosine, plugging in 0. It's like, wait a minute. My last step was plugging in 0. Let me just, wait a minute. Let me just try that. And I just plugged it in. So it can work, but it was gross right away and really, really sloppy. But it did work out. I did it on a separate piece of paper because I did not know what to do. And then I stopped and I was like, oh, wait a minute. So the thing about 14 is I tried this 2 different ways also. I first tried 14 by expanding out x plus 3 cubed. X plus 3 times x plus 3 times x plus 3. And I did the binomial expansion to help me do that. But what eventually I got was this polynomial that was really hard to factor on top. And I knew that, like, all right, plug in -1, I'm going to get 0 over 0. So I know that the limit should exist because there's just a hole there. But I tried multiplying out the top. And I saw what I got. And it was this polynomial that wasn't clearly factorable. It is, but I would have had to, like, synthetic division and, like, try to factor it that way. So instead, and although it can be hard to see initially, what I found easiest and what is almost always easier is just factoring. Where? Oh, so the top there? So the top of 14, so what I recognize is that that's the difference of cubes. X plus 3 cubed minus 2. So, like, that's a cubed minus b cubed. A minus b, a squared plus ab plus b squared. I factored the difference of perfect cubes to see what would happen. And so, like, x plus 3 is a. And so it's x plus 3 and 2. And then x plus 3 squared and 2 times x plus 3 and 2 squared. Same, opposite, always possible. And by factoring instead of expanding, I end up at a point where things are factored so I can divide away the problem. But it's tricky because you have this binomial factor, right? X plus 3 rather than just x or just 3. Once it's factored, divide away the problem. Now I can use direct substitution. But, like, what happened, and I'll go back to it in a second, but just so you see, like, if I try to expand x plus 3 cubed minus 8, if I just tried to expand out the numerator, that's x cubed plus 3x squared times 3 plus 3x times 3 squared plus 3 cubed, and then that minus 8 at the end. A cubed, right? 1, 3, 3, 1, 3, 3, 1 from Pascal's triangle. X to the third, 3 to the 0. X squared, 3 to the first, x to the first, 3 squared, x to the 0, 3 to the third. And so I ended up with x cubed plus 9x squared plus 27x. That's a 3 cubed plus 27 minus 8. So the only thing I can put together is right there. And I got to that. If I expand out that numerator, I end up plus. I end up right there, and it's supposed to be all over what, x plus 1? Right? This is the limit as x approaches -1. So I just did kind of some side work to get there, and I was like, oh, gross. Now what? There's got to be a negative, like there's got to be a factor there of x plus 1. And so I said, all right, fine. Let's do this. Synthetic division. Cool, it factors. So like I had to like get to this point, x squared plus 8x plus 19. And then I could divide away the x plus 1s. I was like, well, that works, but if that was factorable from the beginning, then I should have just been able to factor the top from the beginning. And I didn't actually ever expand it out to get the 8x and the plus 19 or whatever it is, but that's what this would expand to if I expanded. And so that I think by recognizing difference in cubes, I think I saved myself a lot of like side work, or at least a whole bunch of space to get there. A couple different ways to do it. I think I chose the faster way that was just a little bit less intuitive. I think it just took a little bit more thinking. Either way would have worked, but man, I had to go back to like a chapter 2 pre-calc mindset of like, or how do I factor polynomials at a cubic? At least the constant was prime, so there are really only 2 factors I had to look for, 1 and 19, or -1. Yeah, positive or -1 and 19 in the rational roots theorem. This only took 1 skill, factoring different cubes. The other one I had to expand using binomial expansion with Pascal's triangle. Then I had to remember synthetic division. Sure. Page 53. Number, let's back up. If you can factor, that's usually a pretty good place to start. I'm a big fan of looking for ways to factor, because if I can factor, then I can break fractions apart quickly. So GCF up top, and the idea behind factoring, like why am I spending time factoring? Why am I breaking things apart? Well, to keep breaking things apart. Like I want to keep breaking things apart to isolate smaller, easier pieces. And so when I see a sine of x factor up top and I see a 1 minus cosine of x factor up top, I'm like, ooh, those are the numerators I really like from those 2 limits. Let me see if I can find a denominator of x that I can go with. And look, there's an x squared. That's x times x. So I can take the first x, put it under the sine of x, take the second one, put it under the 1 minus cosine of x. There are like, and this is really the only way to ever use both of them at the same time, is to have this exact setup, because that's how it's going to split apart. Sure. Page 56. Perhaps. That's the one we were just talking about. Difference of cubes. X plus 3 cubed and 2 cubed. And so that's one way to do it. I'm just talking about this one. The other way would be to try to expand out that numerator, simplify it, and then factor it. It's just not super nicely factorable in a way that I was hoping for. Now, factoring by grouping didn't work, so I had to anticipate the common factor of x plus 1, top and bottom, which means I'm going to use synthetic division or long division to pull out a factor of x plus 1, which is pulling out a 0 of -1, drop the 1, zigzag multiply, add straight down, zigzag multiply, add straight down, zigzag multiply, add straight down. There's my remainder of 0. So this is 1x squared plus 8x plus 19, which is the leftover factor once I pull out the factor of x plus 1.
So 1 minus 8 is
0.
So is it like sign or like is there different numbers in there? Or,
They would have to be common factors up top. Because it's a 1 minus cosine theta, you've got that polynomial up top. So it would have to be, you have to be able to like pull out a 3.
yeah, like orange and nothing.
Right, so pull out exactly, just like that. So, so factor out the 3. Because, and then there's, well, no, so
Or
not,
3 times 0.
3 times 0, exactly. Because and so, which number is that?
10 on.
Yeah, so then I just pulled out the 3. Yeah. So when you have constant factors, they can be factored out of
If they were different numbers,
like 3 minus 4 cosine theta, we're in trouble. Yeah, that would not work.
But that one, I'm not even thinking about it.
It would not exist. That limit would not
Yeah, I
exist.
was like, what?
There's nothing you can do there to get like, so the problem in all of these is dividing by 0. It's always the issue. So how do I deal with dividing by 0? I either factor out the problem and divide it away somehow, and I get a common factor top and bottom, or I isolate the problem using one of those ones. So last waiting moments here on your last problem, whatever you're working on, and then we will get out of here. If you need this weekend to finish this up, feel free to do that. But if you have it all and you're feeling really good about it, you can throw it up on canvas whenever you're ready. But look what we're plugging in. We're not going over 0. X approaches. Right, so but the issue, look, you have a denominator of x plus 1, you want to divide that away. Because you factor at the top, great, now divide away the problem so you can plug in negative. Yeah. Let's see. Let's see what would happen. So if we look at 1 minus cosine of x. Thank you. Yep, see you guys. Have a good day. Have a great weekend. I will see you Monday. So there's our undefined. Right, so there's our function, undefined at 0, but clearly a limit of going towards 0. And so, right, put that 3 in front there. It's just a vertical stretch, but at 0, multiply by 3, it's still 0. But what if this down here was like a 2? That's a vertical compression. Because what you're really doing,
Like 1/2.
exactly, you are taking 1/2 and multiplying it. That's all you do.
Oh, okay.
The issue that comes up is, okay, well, if that works for putting a number in front of that x, does it work by putting a number in front of this one? Sure. That is a horizontal compression. And so it changes the frequency of cosine. That's all you're doing is you're messing with how quickly, right, sine and cosine go through their cycle. That has a frequency of 3. So I'm going to see 3 full periods of cosine within that normal period of 2 pi. But at 0, nothing changes. So go ahead and feel free to pull out that 3. It's still going to be 3 times 0. But usually they don't do that because it's not uncommon everywhere. That's a much more typical kind of question where you can factor out something so that you are isolating exactly that trig limit and nothing else. That's what I want to do. I want to find exactly that limit if I can. Because that's not really that limit.
Mm-hmm.
Things just change pretty dramatically, right? So we got to be careful. It's weird that it happens this way, because not only did we change the frequency, but now we're changing the function in the denominator, right? Because when I think about rational functions, it's n of x over d of x, right? A numerator function over a denominator function, and what does that do? Well, they work together sometimes. Sometimes they work in opposite directions, kind of messing with what happens. So just by doing that, right?
Oh, is this the class today? This might be the class today. There's been like nobody in our class. So.
This is Friday. People are like, oh, I don't want to go to school.
There was 3 people in my class.
That's great. So there you go. Yep.
I need to ask this. Can I talk to my grandma?
Of course, no,
Talk
no
on the other side.
Yeah, you have a minute and a half. So yeah,
Very responsible.
You don't see any people coming down the hallway.
Knocking pressure over on our way.
I'm just scared.
He's awesome. What's today, the 19th? Where you headed to? Yeah, it has to do with the fact that like you've got this negative cosine, so things that get flipped, and then you've got like it's degree on top is the same as your degree on bottom. Yeah. Yeah, you're welcome. I know, Brad. No, it doesn't feel like we should be here right now. What's up, Jimmy?